So the topic that we'll be doing today is that of momentum. I think it is a completely new topic. Initially, we've done forces and other topics, forces, stability, turning effect. This is another topic that is related to forces, but it is an entirely new concept. So, before going into the scientific details or the formulas of momentum, it's very important to understand the concept of momentum because momentum is a word or it is a term that is very commonly used in sports and in our daily life. Uh, like, for example, a team that has momentum is on the move, like when there is something, an ongoing process that is going very steadily and in a very smooth manner and without any stop to it, we say that, oh my God, it has some momentum. Or that if there is a team that is winning and it is on a streak of winning, we say that it has its own momentum on or is on the move. So anything that is going continuously or has some momentum, or we say that it has some momentum, that there will be a force or something required to stop it. Like there will be some effort required to stop it, to defeat that team, or to, when you're doing something, you are in a zone or you're doing it very smoothly, very efficiently. So there will be something needed to put you on a break. So to break that momentum, we need something, some effort. A team that has a lot of momentum is really on the move and it's going to be very hard to stop. Momentum, in however physics term, is referred to as a quantity of motion that an object has. So momentum is basically, you can imagine momentum as a quantity of mass in motion. That any object with some mass that is in motion, it has to have some momentum that it has. So a sports team that is on the move has the momentum. If an object is in motion, it is on the move, then it has momentum, as I've already said. So this is basically the concept of momentum that we've studied, that any object, anything with a slight mass or with some mass in it will have momentum if it is moving or if it has some velocity. So if we okay, so momentum can also be defined as mass in motion. All objects have mass, so if an object is moving, then it has momentum. It has its mass in motion. That if an object is moving, it has, let's just say we have m, that is a mass, and then we have v, that is a velocity, that is because of its motion. So if we join them, we join mass and motion or velocity, we get momentum. The amount of motion, the amount of momentum that an object has is dependent upon two variables: how much stuff is moving, and by that, how much stuff is moving, how much stuff is moving is the mass part. That we are talking about the mass, that how much mass it has, and how fast the stuff is moving. How fast the stuff is moving, that is also very intuitive. That means the velocity. So VELOCITI, velocity. Momentum depends upon the variables mass and velocity in terms of an equation. The momentum of an object is equal to the mass of an object times the velocity. So now that we knew that these are two things that are that these were two things that we were using to define momentum, both of these were mass and velocity. So now we know that it was basically that the momentum is basically the product of these two, that it is mass multiplied by the the velocity, and it gives us momentum. So in physics, the symbol of quantity momentum is lowercase p. Thus, the above equation can be rewritten as p is equal to m multiplied by v, where m is the mass and v is the velocity. The equation illustrates that momentum is directly proportional to an object's mass and directly proportional to an object's velocity. That if an object has greater mass, then it will have greater momentum, and if it has greater velocity, then it will also have greater momentum. The units for momentum would be mass units times the units of the velocity. So it gives us kilograms meters per second. The standard metric unit of momentum is kilograms meters per second, while these are the SI units. We can also other units are also acceptable, and there can be a variety of combinations of units that can be used. For example, if we do not have a lot of mass and we are talking about a very small grain of rice or something, then we can use mg for mass, and so mg meters per second would be the momentum of that. So it basically doesn't really depend upon the units, but for our sake, the what do you call them, the SI unit, the standard metric units, are kilograms meters per second. So now we okay. So momentum is a vector quantity. As discussed in earlier unit, a vector quantity is a quantity that can only be fully described by both magnitude and direction. So momentum is a vector quantity. Now, if you think about it, that's very easy to understand um, because of one thing, because um momentum has this quantity inside that we account, which is a very clear vector quantity, and that is velocity. So momentum is a vector quantity as discussed in an earlier unit. A vector quantity is a quantity that is fully described by both magnitude and direction. So the vector part of momentum comes definitely from the velocity. So whatever the direction of velocity is going to be is the direction that was of momentum, or that is of momentum. So the direction of momentum vector is the same as the direction of velocity of an object. Previously, we have also studied resolving forces. Similar is the case if we are given momentum, we will also resolve that similarly. The momentum vector will be in the direction of the velocity, and then if you're asked to draw them or to solve them, so that's how we are going to find the resultant by using the three laws that are of triangle law, parallelogram law, and the last one is that of polygon method. So momentum is a useful quantity to consider when bodies are involved in collisions and explosions, because mass of an object can change. If in an explosion, one big huge object can turn into debris of very small masses in an explosion. So it is defined as the mass of a body multiplied by its velocity and is measured in kilogram meters per second, or we can also say Newton second. Now, this is another important thing, that we can also say Newton second. Why can we say Newton second? Newton is not is the unit of a very important quantity that we have very thoroughly discussed, and that is force. So, does that mean that momentum is related to force? Well, yes, momentum is related to force, and we are going to study about that too in some time. So, now moving forward, um, conservation of momentum. When two or more bodies act on another, as in a collision, the total momentum of the bodies remain constant, provided no forces act. Example, friction. So conservation of momentum is when two bodies they act in a collision and that the total momentum of the bodies remain constant. Well, if you imagine that we do it in this form, that there is this ball and there is this ball and then there is this ball. So what happens is that this ball hits this ball and then this ball hits this ball. Now, if in the end the conservation of momentum goes the that the momentum that this ball initially had equals to the momentum that this ball, this last ball plus this ball had after the impact. If the sum of all the end momentums of all these three after the impact equates to the initial momentum of this initial ball, then that means that the momentum has been conserved and that the bodies had conserved, conservation of momentum collision. So, as an example, suppose a truck of mass 60 kilograms moving with velocity 30 meters per second collides and couples with stationary truck of mass 30 kg. So, this is the diagram. The two move off together with the same velocity v, which we can find as follows. This is how they are moved together afterwards. The two move off together with the same mass, yes. Okay, the total momentum before is. Okay, so now this is a very repetitive question and a type of question that does occur in exams very often. So what happens is that initially this block or this card, it is moving with some velocity, right? So what is the momentum of this um, truck or this whatever card? So the momentum is going to be mass times velocity, so we multiply 60 times 3. Okay, now the first thing that you should do when you're doing these questions of conservation of momentum, it is very important to write down the objects that we are dealing with. So the first object that we are dealing with is this 60 kilogram card, and the second object that we are dealing with is this 30 kg is this 30 kg another cart or whatever this thing is, stationary truck. So what happens is that I'm gonna write it like this. So one of the objects is 60 kg stuff and the other one is 30 kg. So the 60 kg, this is initial. I'm gonna write initially how we are, like, at what state we are. So this is initial. It was just okay to write initial. And then F is for final, right? So this is just considered that there's this is a 60 kg, so that we don't use it as a quantity. This is just to define the subject. So initially, the 60 kg card had 3 meters per second and the other was at 0. Now what we have to do is that we don't know that what is the final velocity of these two. Okay, so the total momentum before is 60 multiplied by 3, which is written over here, plus 30 multiplied by 0, which is 180 kilograms meters per second. So the total momentum after should be equal because it is supposed to be we are doing the conservation of momentum. So we're concerned with momentum and we're considering that no external force is acting on it. There is no friction factor involved. So the total momentum after is equal to 60 plus 30. Now, why did we do this? We did this because both of these combined together after the collision. They are now joined together. They're not separate ways. They are one body. So now we have this 90 kg block or whatever this truck is, that multiplied by velocity, that is not given to us. So 90 kg multiplied by v is equal to 180. That gives us 2 meters per second for the velocity for them to be equal. Momentum is conserved in explosions such as the ones that occur when a rifle is fired. Before firing, the total momentum is 0, since both the rifle and bullet are at rest. During the firing, the rifle and bullet receive equal but opposite amounts of momentum, so the total momentum after the firing is also 0. Now, if you look at it, this is a gun. If you shoot it, now, the bullet goes really, really fast, but it also has mass that is really slow. And there's always this recoil that you feel that the rifle or this gun has whenever you shoot something which is towards the backward side. So this huge mass has a lower velocity or a lower impact in the opposite direction than the bullet has in the forward direction with very high velocity because of its very less mass. For example, if a rifle fires a bullet of mass 0.01 kilograms with a velocity of 300 meters per second, forward momentum of bullet is equal to this. Now, this should be equal to the backward momentum of the gun or the rifle. So, backward momentum of rifle is equal to 3 kilograms meters per second. If the rifle has mass m, it recoils, kicks back with a velocity v such that mv is equal to 3. So we're imagining that this rifle has a mass of 6 kilograms. So if we divide 6 equals, if we do, sorry, 6 multiplied by v is equal to 3. So velocity is 0.5 meters per second. So that impact at that point, the momentum is conserved, but both of them, they moved in opposite directions. So it got cancelled out. Okay, now rockets and jets. If you release an inflated balloon with a neck open, it flies off in the opposite direction. So that is another recoil situation that is happening. The balloon moves in forward direction, but the air that is escaping out, it is moving in the opposite direction. So it flies off in the opposite directions to that of the escaping air. This is the principle of rocket and jets. This is a similar way how rockets and jets work, that this air is basically moving downwards and it is basically helping and propel upwards. So in both, a high velocity stream of hot gas is produced by burning fuel, and that leaves the exhaust with large momentum because the velocity is really, really high. So the momentum is large, and that's why it helps us move. A rocket or a jet engine itself requires an equal forward momentum. Space rockets carry their own oxygen supply. Jet engines use the surrounding air. So, jet engines use the surrounding air, and space rockets carry their own oxygen supply, and that multiplied by H2 reaction produces water, and then that helps them propel or move. Now, how is force and momentum? How are they related? Because we already studied that momentum does have this, what do you call it? Momentum does have this really important link or aspect that is related to, what do you call them? The force, because the units of momentum we've already studied, they're also Newton second. How is that possible? Now we are going to look at that, and how that happens is like this. So if a steady force F acting on an object increases its velocity from u to v in time, the acceleration is given by this. That acceleration is equal to final velocity minus initial velocity divided by time, and that gives us acceleration. Substituting from a in F is equal to ma. Now we are, instead of for a, we are introducing m. We are multiplying that acceleration with m, and we are equating it to force. Now if you look closely, what we have done is that I had a over here, I just attached m to it. So it is now F is equal to ma, and we know F is equal to ma is equal to, sorry, ma is equal to F. So now I don't need this equation because we are going to also multiply m over here. So I don't need this equation. Okay. Now what is, it's basically multiplying m multiplied by v minus u divided by t. So mv minus mu divided by t. What is mv? Mv or mu, both of them are momentum. So what this tells us that the rate of change of momentum is equal to force. The rate of change of momentum is equal to force. This is the final momentum with the v velocity. This is the initial momentum with u velocity. And the rate of change of these momentums is called force. Therefore, force change of momentum time is equal to rate change of momentum. force change of momentum time is equal to rate of change of momentum, right? This is another version of Newton's second law. So this is another version of basically F is equal to ma. We use the same definition. We just we're literally just instead of using A as is, we just used A as is V minus U by T. So it's not another law. It's simply Newton's second law that we have already studied so many times. Okay. So in sports, we do have these concepts of impulses and collision times and forces. Now, what is that? Now, before getting to that, it is also important to know um, what exactly impulse is. Impulse is basically change in momentum. It is force times force times force multiplied by time. Sorry. So change in momentum, final momentum minus initial momentum is equal to impulse. So the good cricketer or tennis player follows through with the bat or racket when striking the ball. The force applied then acts for a longer time. The impulse is greater. Impulse means the change of momentum is greater, and so also is the gain of momentum. Impulse is change in momentum and is also equal to force multiplied by time because the force that the mm, batsman or the cricketer hit, hit hit the ball with was very high, hence the impulse was greater. When we want to stop a ball moving, such as a cricket ball, however, its momentum has to be reduced to zero. An impulse is then required in the form of an opposing force acting for a certain time. While any number of combinations of forces and time would be given in a particular impulse, the sting can be removed from the catch by drawing back the hands as the ball is caught. So there are a lot of ways in which we can multiply the force with that time in order to find the impulse that will be needed for the ball to stop. But what we simply do is that it just the the fielders or whatever they are, they just catch the ball and that applies the impulse to make it stop. So a smaller average force is then applied for a longer time. So it's basically a game of force and time. So if you're using it for a longer time, then a smaller force will be required because it's a product and they're directly proportional to impulse. And if we apply a very large force for a very less time, as we did when we were hitting the ball in the first place, so that is also another way to apply a large impulse. So now we are going to summarize what we have studied. So which object has the higher momentum? Now we know that momentum is basically just mass multiplied by the velocity. So multiply 60 grams, multiply by 75, and 3 kilogram multiplied by 1.5. Both of them have equal momentum. The product is 4.5. So although it may seem like that the brick is heavy or that the ball is small, so it is moving at a higher speed or just making assumptions like that. It's very important to consider both of these quantities, mass and velocity, at the same time, and then taking the product in order to comment about momentum. So both the tennis ball and brick have the same momentum. Even though the brick is much heavier than the ball is traveling much faster than the brick, which means on impact they would both exert a similar force depending on the time it takes to reduce each object's speed to zero. Okay, conservation of momentum, we've already studied that. In absence of external forces such as friction, the total momentum of a system remains the same. So, in conservation of momentum, we don't really have a final impulse, a change of momentum. But however, we talk about one body or one subject only, then definitely we do have um, a change of momentums. But as a system, as a whole, there is no change of momentum. So this means that in a collision, the sum of momentums before the collision will be same as the momentums after the collision. In the above diagram is this diagram. Total momentum before and the total momentum after must be equal to zero. So in this, again, this small ball hit with initial velocity m, and then both of them traveled in this direction and they should be equal. Now, why do we have this sign minus? Because we are dealing with vectors because we have velocity involved. So it's very important to consider the direction because this moves in opposite direction. So we are have a minus sign. Initially, it's moving in towards the right, and we are considering that direction as positive. So that's a positive here. We don't have any negative here. However, this is moving in opposite direction. This ball, so we are putting a negative sign over there. Okay, so moving forward. Note that because the red ball is traveling to the left after the collision, its momentum will be negative, hence the minus sign is the above the equation. Now, impulse. When a resultant force acts on a mass, the momentum of mass will change. The impulse of force is equal to the force multiplied by time for which it acts, and it is also equal to change in momentum. So F multiplied by T is equal to mv minus mu, where u is the initial velocity and F is the final velocity. This is it for this topic.